The SYNAPS-I project stands for the Synergistic Neutron and Photon Science Intelligence. It's a project that brings together X-ray and neutron facilities to build a foundation model, and this foundation model aims to accelerate the analysis over 100 times, allowing them to do real-time analysis and also automate experiments.
SYNAPS-I enables real-time analysis of X-ray imaging data. We can take an image as acquired on the detector and invert that into an image of the object that we just measured.
The hard X-ray nanoprobe beamline, where the SYNAPS-I project is demonstrated, is jointly operated by the Center for Nanoscale Materials and the Advanced Photon Source. This partnership really makes this beamline so special. CNM brings expertise in synthesizing nanoscale materials, where APS offers the ideal X-ray platform to characterize them.
Prior to the SYNAPS-I project, scientists would collect these large data sets and go back afterward, once they've returned home, and spend months or weeks to analyze them. Now what we're able to do is give that analyzed result straight to the beamline scientist or the experimenter in real time, such that they can use that information to inform their next planned experiment. This is a critical driver of scientific discovery and innovation because it allows experiments to be done in situ or operando in a condition where the sample may be dynamically changing throughout the course of the measurement. So without this artificial intelligence component, we would never be able to achieve a real-time live feedback on the experiment.
Our beamline is one of the beamlines that benefits most from the APS upgrade project. With drastically improved coherence and brightness, we can now use a broader portion of the beam, which increases the usable flux at our beamline by a factor of 20. The kind of experiment that used to take a day on our beamline now takes just an hour, and that is exactly the high throughput imaging capability the SYNAPS-I project is designed for.
The specific technique that we're starting with for this foundation model is called tachography. And it's a technique that specifically takes advantage of the new and upgraded advanced photon source. It's what's known as a coherent imaging technique. It takes advantage of this extremely bright and coherent source to allow you to image things at very high resolution, so very, very small scale, on a few nanometer scale, but over large areas.
One of the unique capability of tachography is that it can uncover fine details smaller than the size of the X-ray beam. In a sense, it takes a blurry image and enhances it to reveal details you cannot see directly. But that also raises an important question: how can you trust these added details, especially if it's coming from an AI? And this is where our beamline comes in. With our nanoscale beam, we can directly map out the nanoscale objects and use that to validate the tachographic reconstructions.
And so this technique produces a lot of data very quickly. And this foundation model does this inversion between what we measure and what the sample looks like. So it's image-to-image mapping, and it does this in real time, giving users an immediate insight into what is happening in the material.
Prior to the SYNAPS-I model, this type of dataset would often require an expert in inverse problems or computational imaging to analyze in a reasonable amount of time. For the broader scientific community, we're now looking at a much higher degree of accessibility to this type of experiment. Chemists, material scientists, physicists, and biologists can now focus on their specific samples. This means that they can spend their time designing materials and innovating.
We trained this foundation model on over 1,000 GPUs at the Perlmutter cluster at Lawrence Berkeley. We fine-tuned this on the Polaris machine at Argonne before deploying this at several of the beamlines at the APS to do this real-time analysis. And we're using this now to look at advanced technological materials like semiconductor chips, as well as quantum devices. So I think this is a perfect example of what we can achieve when we bring together leadership computing, frontier AI, and advanced experimental facilities like the Advanced Photon Source at Argonne. SYNAPS-I is part of the US Department of Energy's Genesis project. It is a cross-facility effort to build a foundation model for X-ray and neutron sources. Demonstrations were performed at the Advanced Light Source at Lawrence Berkeley National Lab, the Advanced Photon Source at Argonne National Lab, and the National Synchrotron Light Source 2 at Brookhaven National Lab. Future demos will expand to all of the DOE light and neutron sources in the United States.